All right, we're going to go ahead and finish up our introduction to logarithmic functions. In this video, we're going to talk about graphing logarithmic functions, and then we're also going to talk about solving exponential and logarithmic equations. All right, we're going to start by graphing. And for me, when I talk about logarithmic functions and graphing logarithmic functions, I do like to take advantage of the fact that it is the inverse of the exponential. And so, for instance, if I want to graph this one over here, well, this is going to be using transformations. And so before I look at it using transformations, I want to look at just the basic logarithmic equation. But as I said, for me, I don't like thinking in terms of logarithms. I prefer thinking in terms of exponentials. And so that's what I'm going to start with. Anytime I'm asked to graph a logarithmic equation, I always start with the exponential. So let's go ahead and start with that. So for this one, we're going to go ahead and create our tables. Remember that for exponentials, we like -1, 0, 1. And because it is a base 2, I'm just going to go a little bit further, and I'm going to go ahead and go with 2 as well. All right, so remember that 2 to the -1, we want the reciprocal of 2, so that's going to be 1/2. Anything to the 0 power is 1. Anything to the first power is itself, so we get 2. And then 2 squared is 4. For this, remember that we also have a horizontal asymptote of y equals 0. All right, the next thing that I'm going to do is I'm going to go ahead and do the inverse function. And so for our inverse function, remember that all we're going to do is we are going to flip-flop our variables. And so my x's in the h of x become the y's. So we have -1, 0, 1, 2. And my y's become x's. So we have 1/2, 1, 2, 4. And we also have an asymptote. Y's become x's become y's become x's, and so my asymptote is now going to be x equals 0. All right, and then for the actual function that we want, capital H of x, we have inside, we have a horizontal shift. And remember, horizontal, we always want to do the opposite of what it says. Here, since it says x minus 2, this means that I want to add 2 to my x's. So if we add 2 to 1/2, we get 2.5. We don't have anything on the outside, so all of my y's will stay the same. If we add 2 onto 1, we get 3. If we add 2 onto 2, we get 4. And if we add 2 onto 4, we get 6. All right, so now let's go ahead and see what this looks like, okay? I'm going to graph all 3 of these, okay? But remember that the focus is on capital H of x. All right, if we start with our exponential function, we have -1, 1/2. We have 0, 1, 1, 2, and 2, 4. And this is an exponential, so it is going to curve and go up this way. All right. Now we're going to go ahead and look at the basic logarithm. And so when we do this, we have 1/2 -1, 1, 0, 2, 1, and 4, 2. And so it looks like this. And again, if you tilt your head sideways and squint your eyes, you should see some symmetry between these two graphs. Okay, now we want to do the shift. Now, when we look at our asymptotes, for our exponential, we have an asymptote at the x-axis. Remember, this is y equals 0. For our basic logarithm, we have an asymptote of the y-axis, or x equals 0. And when we shift it, we also have to shift the asymptote. And so my asymptote is also going to be shifted, and it's going to be x equals 2. So my asymptote is going to move to here. When we graph this, we have 2.5, -1, 3, 0, 4, 1, and if we extend further over, let me get rid of that. Move the y equals 0 over here. And then we have 6, 2. And so this is going to be my graph for the logarithmic function. All right, let's look at one more example. Okay, for b, we have k of x equals log of -x plus 1. Again, the first thing that I want is I want to go ahead and start by my table for just the basic logarithm. And before we do the basic logarithm, I want to do my exponential. This is log base 10, and so my exponential is going to be 10 to the x. And so again, we're going to go -1, 0, 1, and those are the only ones I'm going to work with. We get 1/10, 1, and 10. -1, we want the reciprocal of 10. Anything to the 0 power is 1, and anything to the first power is itself. All right, now we can go ahead and talk about the basic logarithm. We want to flip our x's and our y's, so our y's become x's, our x's become y's, and we have our basic logarithmic function. And then finally, we want the actual function that we wanted to graph. And so my actual function, let's see what we have here. All right, the first thing that we have is we have this negative on the inside. And so remember, the negative on the inside is going to be a reflect. And again, this is going, since it is inside, this is a horizontal reflect. And if we're doing a horizontal reflect, remember we're going side to side, which means this is about the y-axis. Now, in terms of what we're going to do, remember, all this means is we want to change the sign of our x's. So this is now going to be -1/10, -1, and -10. All right, the other thing that we have going on here is we have a +1 on the outside. It's outside my function, which means it is vertical. It is an addition, which means that it is a vertical shift. And remember, because it is vertical, we do what it says. So we want to do our y's +1. And so if we do this, we get 0, 1, and 2. All right, let's talk about our asymptotes again. Remember, for our basic exponential, we have a horizontal asymptote of y equals 0. When we convert this into a basic logarithm, we have a vertical asymptote of x equals 0. And it is going to stay the same because notice that we don't have any moving left or right. We just reflect it, and the reflection does not affect the vertical asymptote. And so we still have a vertical asymptote of x equals 0. Now for this one, all it gave us that it wanted was k of x. It did not ask us to graph anything else, and so this is all we're going to graph. And so if we go ahead and graph this, and we're going to do the best that we can. Remember that as our bases get bigger, this gets harder to draw by hand. But we'll go ahead and try this. Okay, so we have negative. Oh, and I went the wrong direction. Okay, let's see what we got here. All right, we have -1/10, comma 0. So this is going to be somewhere right about here. We're going to try to get close to our axis. And we'll go right there. All right, we have -1, 1. That one's okay. And then the last one we have is -10, 2. And so that's going to be over here. Now, as you see, this gets a little difficult to draw because our numbers get really, really small very fast. And they get really, really big very fast. But we have this. We have our vertical asymptote, and so if you notice, we are still in reference to our x-axis, or sorry, our y-axis. And so we do still have the asymptote of x equals 0. All right, and that's going to be our graphing. Now, as I said, me personally, this is the way that I do like to do it graphically. That way I can kind of see how things change between the exponential and the logarithm. Of course, on your homework, these are all going to be multiple choice. But remember that you do want to understand what's going on. In order to understand this, I do recommend creating these tables and doing it by hand. All right, the next thing that we want to talk about is we are going to talk about solving basic exponential equations. All right, so the first thing that we're going to do is very similar to what we've talked about whenever we've talked about, any kind of special equation, except for linear and quadratic and rational. We've always wanted to isolate the key thing. For instance, if it's a square root, we want to isolate the square root. If it's a cubic, we want to isolate the cube. And so these were kind of our basic strategies that we had. And we do the same thing for exponential. So the first thing that we want to do when we talk about solving exponentials is isolate the exponential. If we have anything on the outside, go ahead and move it to the other side. After that, we have one of two strategies. The first one that we want to try is, can we write both sides of the equation with the same base? If we can, we should. After that, we can do what we were doing in the last video, which is cancel the bases and solve the resulting equation. Now, it is possible that you cannot write with the same base. And so if you cannot write with the same base, then what we do is just like when we talked about how do you get rid of a square root, you square it. How do you get rid of a square? You square root. Well, we already know what the opposite of an exponential is. It's a logarithm. And so to finish this off, if we cannot write with the same base, what we're going to do is take the logarithm of both sides, and then we finish solving the resulting equation, if possible. All right, so let's go ahead and jump into some examples of this and see what we can do. All right, we're going to start with example A. Example A, we have 10 to the x equals 0.001. All right, so what we have here is, I'm going to leave my 10 to the x alone, but I do want to come over here to my 0.001. What this is this is 1 over 1,000. When we look at decimals, what we do is whatever the number is after the decimal becomes the numerator. The denominator is going to be 1 followed by the same number of zeros as we have column values. And so here I have 1, 2, 3 columns after the decimal point, which means that in my denominator, I want 1, 2, 3 zeros. Well, 1 over 1,000, we can write that as 10 raised to something. This is 10 to the negative 3. 10 cubed is equal to 1,000. And then if we flip it to the bottom, we know we want a negative exponent. All right, now that we have our bases are the same, we can cancel them. And we are left with x equals negative 3. And we're done. All right, let's look at a couple other examples. Let's come over to example B. Example B, I cannot write 55 with a base of 10. And so this is going to be an example where we want to take logarithms. Because we have base 10, I am going to take the common log. So I'm going to go log base 10 of 10 raised to the x equals log of 55. Remember that these two notations represent the same thing. For the left side, I am writing it with a base 10 just so that we can see that they do cancel. And we are just left with x. On the right side, well, I'm going to have to do my calculator for this one. And so we are going to input in our calculator log of 55. All right, when I do this in my calculator, I get 1.7404. When we do logarithms, we usually like to go out 3 or 4 decimals. And so, of course, when you're doing homework and it asks for an approximate value, make sure that you check in terms of how far it wants you to go out. All right, and the last one for our common log, or for our base 10, is we have 10 to the x equals -1. And for this, we have no solution. Okay, remember that exponentials have a range of 0 to infinity exclusive. -1 is not in that interval. Exponentials, no matter what number we plug into x, we are going to get a positive answer. And so it is never equal to -1. I do encourage you to put this in your calculator. And so, again, we can take, we're going to take the log of both sides. We have log 10 of 10 to the x equals log of -1. And if we plug this into our calculator, let's see what we get. When I plug this into my calculator, I get non-real answer. Okay. And so that means that this is not a real number. This is a complex number. And we don't talk about complex numbers in terms of logarithms. And so that's why we say no solution. Now, if you do get answers that are, if you do get something else, that means that your calculator is most likely in complex mode. And you should see somewhere in there eyes running around. If you see eyes running around, that means no real solution. All right, let's keep going and try a couple more. All right, the next one we have is example D. We're going to start getting into a little bit more complex examples. Okay, for this one, the thing that I noticed first off is that I do have something outside my exponential. And so the first thing I want to do is I want to isolate my exponential. And in order to do that, we're going to go ahead and divide both sides by 4. All right, we get 10 to the 3x equals 6. This is another example where I cannot write them with the same base. And so we're going to go ahead and take the logarithm. So I'm going to take the common log of both sides. On the left side, these cancel. I am left with 3x equals log of 6. And then we can finish solving for x. We're going to divide by 3. And our exact solution is log of 6 divided by 3. Okay, now we want to go ahead and approximate this. And so we're going to go into our calculator and type this in. And what I get is 0.2594. This is a rounded answer. Now, if you did not get this, make sure that when you are doing this, it opens up a parenthesis after the logarithm. Make sure that you do close that parenthesis before you divide by 3. All right, that's example D. All right, let's come over to something that is not a common log. All right, so the first one, we have 3 to the x equals 1 over 27. Okay, for this, we are going to use our first strategy. Later on, we'll get into more complicated exponential equations, but this is not base 10, it's not base e, and so we do need to go ahead and write with the same base. All right, for this one, 1 over 27, I can write this with a base of 3. 3 cubed is equal to 27. And I did take a reciprocal, so I do want a negative exponent. Since our bases are the same, we can go ahead and cancel them now. And what we get is x equals negative 3. And we're done. All right, our next example, we have e to the x equals 5. Because it is an e, we do have a special logarithm that we can use for this one. And 5 cannot be written as e to something. So what we're going to do is we're going to take log base e of both sides. On the left, I'm going to do log base e. But remember that log base e is the same thing as natural log of 5. On the left, these cancel, and we're just left with x. And on the right, we have natural log of 5. This is a calculator problem now if we want an approximate answer. And so let's plug this into our calculator and see what we get. When I put this in my calculator, I get 1.6904. All right, a couple more examples. I think I got one more. Is that right? Okay, we got one more. All right, let's go ahead and look at this last one. Okay, for this last one, we are going to start. So I'm going to go ahead and add 7 to both sides. We get 27. I want to divide by 3. We get 2 to the x is equal to 9. I'm not sure if we're going to see examples like this in this section. We haven't really talked about everything that we need to do, and I am wondering if maybe I did a typo. But I'll go ahead and show you how we can do this. I cannot write 9 with a base of 2. Now, we can still go ahead and take logarithms of both sides. I can't do log base 2 because, again, we're going to run into issues because this is going to be a calculator problem. But we can take either the common log or the natural log of both sides. And it does not matter which one you do, as long as you do the same one on both. Next section, we're going to talk about kind of what we do from here. But what we have is when we take the logarithm of both sides, or when we take a logarithm, we can move the variable down to the front. And again, I'll go over this in more detail in the next section. And so what we get is x log of 2 equals log of 9. And from here, what we have is x times a number. It doesn't matter what the number is. It is just x times a number. And just like when we multiplied x times any other number, in order to get x by itself, we are going to divide by whatever that number is. And so what we get here is x equals log of 9 divided by log of 2. This is a calculator problem now. And so if we go to our calculator and type this in, what we get is 3.1699. All right, that takes care of that one. All right, and that takes care of solving our exponentials. Again, this one, I'm going to say don't worry about it too much. As I said, I think I either have a typo because this does not belong in this section. We'll look at ones like this in a little bit later and talk about it in more detail. All right, let's go ahead and continue. The second thing that we want to solve is we're going to talk about solving basic logarithmic equations. All right, just like with our exponentials, the first thing that we want to do is we want to isolate the logarithm. If we have anything on the outside, we want to move it to the other side. And then the next thing that we want to do is we want to convert it into an exponential. And so remember that our conversion is log base b of x equals y. We can convert it into an exponential by using our around the world trick. We get b to the y equals x. Once we have done this, we can go ahead and finish solving our equation. And the last thing that we need to do is we do need to check our solution. I don't think we're going to see any examples here of this. We'll see them a little bit later. But just like when we talked about our rational equations, if you recall, rational equations, the only thing that we care about is does it make the denominator 0? We do a similar thing with logarithms. All we want to do is confirm that the inside is positive. All right, so let's go ahead and look at some examples of this. All right, example A, we have log of x equals 3. The first thing that I'm going to do is I'm going to rewrite this with a base. This is a common log, so this is log base 10 of x equals 3. And then we can do our around the world. So we get 10 to the third is equal to x. And we can simplify this. 10 cubed is equal to 1,000, and you're done. When we do our check, if we plug this into our logarithm here, is it a positive number? It is, and we're done. All right, let's go ahead and look at a couple other ones. All right, example B. We want to do basically the same thing. I'm going to start by rewriting this as log base 10 of x equals -2. We do our around the world thing. We get 10 to the -2 is equal to x. 10 to the -2, we want to move it to the other side of the fraction bar, and we want to square. And so what is 1 over 100. Check step. If we plug this in, is it positive? It is, and you're done. All right, last one that we have for this row. We have log of x equals 2.7. I'm going to start by rewriting this with a base. So this is log 10 of x equals 2.7. And we do our around the world thing. So we get 10 to the 2.7 is equal to x. And this is a calculator problem. So we're going to go to our calculator and plug this in. And when I plug this into my calculator, I get 501.1872. Even if you don't know what 10 to the 2.7 is, you can still kind of check to make sure that your answer makes sense. 10 squared is 100. 10 cubed is 1,000. And so we want a number between 100 and 1,000. And that is what this one is. All right, those are some examples with common logarithms. Oh, we got one more. Okay. So let's go ahead and look at our last one. All right, this one, we do have stuff on the outside. And so the first thing that I want to do is I want to isolate my logarithm. I'm going to divide by 5. And I'm also going to go ahead and rewrite this as log base 10 of 2x. I'm also going to go ahead and simplify this, and I'm going to convert it to a decimal. And if we divide by 5, 16 by 5, I do believe that we get 3.2. We can go ahead and now do our round the world. So we get 10 to the 3.2. Equals 2x. I can go ahead and divide by 2. And so what we have for our exact answer is 10 raised to the 3.2 divided by 2. And this is a calculator problem now. So let's go to our calculator and plug it in and see what we get. I get 792.4466. All right, and same thing, we can think about this. Okay, 10 cubed is 1,000. If you divide that by 2, you get 500. 10 to the 4th power is going to be 10,000. And if you divide that by 2, you get 5,000. And so our answer should be somewhere between 500 and 5,000. 792 does fall within that range, and so we are good. All right, let's look at a couple others. All right, we're going to go ahead and get into some other bases now. And so, for instance, we have log base 2 of x equals 5. It already has the base, so we don't have to worry about that. And we're going to go ahead and start with our around the world. So we get 2 to the 5th equals x. All right, if we do 2 to the 5th, we should get 32. We get 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, and there are 5 2's, and so we do get 32. right, let's look at a couple other ones. F, we have log base 5 of x equals -2. And so we're going to go ahead and do our around the world. We get 5 to the -2 equals x. And so for this one, we have a negative exponent, so we're going to do 1 over. And if we square 5, we get 25. And that's our final answer. All right, and then the last couple ones that we have. All right, we have natural log of x equals 4.3. Again, this is one of our special logarithms. So the first thing I'm going to do is rewrite this as log base e of x equals 4.3. And then we can do our around the world trick. We get e to the 4.3 equals x. Now it doesn't matter. This one is, whenever we have e's, this is going to be a calculator problem. And so let's go to our calculator and type this in. Again, the e is above the ln on your calculator. And what I get is 73.699. All right, and last one. All right, this one we have some stuff on the outside. So the first thing that I want to do is I want to isolate my logarithm. I'm going to go ahead and divide both sides by 3. We get log base 2 of 5x equals 3. We can now do our around the world. So we get 2 cubed equals 5x. Two cubed is 8. We can then divide by 5. You can leave it as a fraction, or you can go ahead and write it as a decimal. 8 divided by 5 is equal to 1.6. And that's what we get. When we plug this in, if we multiply 5 times 1.6, we get 8. And is 8 a positive number? And it is. All right, that takes care of our basic logarithmic equations. The last thing we want to do is we want to look at an application problem. All right, so we have the number of species of tropical birds on islands of different size x near New Guinea can be modeled by f of x equals 39 plus 13 log of x, where x is in square miles. We're going to say that I have a typo here. I was wondering why I was having a hard time understanding this problem. This is going to be f of x. Okay, so f of x is our number of bird species. Okay, part A, let's see what we can do here. It says, if the number of square miles x of an island increases tenfold, how many additional species of birds are there? All right, so let's talk about how we're going to figure this out. Okay, I'm going to start by plugging in 1 for x. Okay? All right, if we plug in 1 for x, what we get is if we have a island that is 1 square mile, if we plug this in, we get 39 plus 13 log of 1. And you can plug this in your calculator and see what happens. But log of 1 is 0. And so what we get is 13 times 0, and that cancels out. And we have 39. Now, when we look at the phrase increases tenfold, this means we want to multiply by 10. And so I'm going to go ahead and multiply 1 by 10, and we get 10. And let's see what happens when we plug in 10 to our function. If we plug in 10, remember this is log base 10 of 10, and this is basically to the first power now. What we get is our log and our 10 cancel, and we are left with 1. And so this becomes 39 plus 13 times 1. And what we end up with is 39 plus 13, which is 52. And so as we multiply, and we're going to see the same pattern as we go along. What we're going to see is as we multiply, if you multiply the area by 10, the number of bird species increases by 13. When we talked about exponential functions, remember that on our x side we were adding as we went through our table. We went 0, 1, 2, 3, 4. And our y's, what they did was they multiplied. We multiplied by 2 as we progressed through our table. And so when we talk about logarithmic functions, we're reversing that. We're going to be multiplying our x's, and we're going to add on our y side. All right, the last thing we want to do is we want to determine the size of an island that might have 50 different bird species. All right, so this is going to be bird species, which is an f of x. So we're going to plug that in for f of x. We get 50 equals 39 plus 13 log x. All right, the first thing that we want to do is we want to isolate our logarithm. So I'm going to subtract 39, and we get 11. I want to divide by 13. And what we have is of x equals 11 over 13. I'm just going to flip my equation around and put my base in there. And so if we go ahead and do our around the world trick, we get 10 to the 11 divided by 13 equals x. And it's now a calculator problem. Now for this one, make sure that when you input this, make sure that your 11 over 13 is in the entire exponent. And what I get is I get 7.02. There's some other decimals, but we are talking about square miles, and so I think that going in to the nearest hundredth is good enough. So we're going to go 702 square miles. That does make sense because we said that if we looked at our previous problem, when it was 1 square mile, it was 39. When it was 10 square miles, it was 52. And 50 falls in between there. It's a little bit closer to 10, or to 52, and so our answer should be a little bit closer to 10. All right, that finishes up this section. And so in the next section, we're going to go ahead and talk about properties of logarithms. And then we're also probably going to do some more solving of exponential and logarithmic equations that are a little bit more complex.